was rather hard to come up with an example program to demonstrate Bayes' rule, as all the useful examples I could think of either required technical knowledge beyond my level of expertise, or would have been too complicated to explain in 20 minutes or less, or both. So in the end I bottled out and came up with another made-up medical example. The result is a rather short program that nevertheless does show how Bayes' rule can be used to draw conclusions from data. In our fictional society, there are 3 diseases you can suffer from: Saturday night fever, toxic gnome syndrome, and mousepox. These diseases manifest in some combination of 3 symptoms: the sniffles, the staggers, and the shakes. The table that you see here shows the screen layout indicating how common different combinations of these symptoms are for different diseases, with a 4th line added that shows that even people in rude health sometimes have the sniffles, staggers, or shakes. Although I've had to split that table into 2 in order to fit it onto the screen, consider it as one long table with 4 rows and 8 columns, one for each combination of the 3 symptoms. The screen also has 3 checkboxes labelled sniffles, staggers, and shakes, so that you can tell the computer program about the patient who is right in front of you and whose ailment you are trying to diagnose. Take a look at his sorry state, click the relevant box or boxes, and click on Diagnose. The program then gives you the probabilities that the patient has each of the 3 diseases. The cells of the table are input fields with default values, so that you can alter the numbers and re-diagnose to see how your changes affect the different probabilities. The name of each field starts with the initials of the disease in question: SNF, TGS, MP, or H for the last line, indicating healthy, plus the combinations of symptoms encoded as a 3-digit binary number. First digit is 1 if the symptoms include the sniffles, or 0 if not. The second digit is 1 if the symptoms include the staggers, and the last digit is set to 1 if the symptoms include the shakes. Putting these 2 parts together, separated by an underscore, gives the name for each input field. So the default value in field TGS_010 shows that 10 patients with nothing but the staggers have been diagnosed with toxic gnome syndrome, as shown, just as 28 people with the staggers and the shakes turned out to have the dreaded mousepox. You'll recall from the lecture accompanying this example that the equation for Bayes' rule gives you the probability of a particular statement being true. I called the statement H for the hypothesis, assuming that we see a piece of evidence, E. Here's the equation again, except now we want the probability of a particular disease, so I have used the letter D. We want P of D given E, the probability of any particular disease given the evidence of what symptoms are present. In this equation, P of D is the prevalence of the disease in society, i.e. the probability that any random person chosen from society has that disease. Very low, I hope. P of E given D is the probability of the evidence assuming that the disease is present, i.e. the probability that a known sufferer of the disease will show symptoms that the patient is actually showing. P of not D is the chance of any person chosen at random not having the disease. It's the vast majority of people in the population who are non-sufferers. P of E given not D is the probability that any non-sufferer of the disease would show the current symptoms. After all, it is possible that people could have the staggers and or the shakes and or the sniffles without having the disease that we're considering. It includes all the people with one or other of the other 2 diseases, but not D simply means not this particular disease. These probabilities can be calculated from the figures in that table. The program reads the checkboxes to construct a particular combination of symptoms. That's the E referred to in the equation. All the people in society, including the healthy ones, are the people in the column headed by that combination. We will need the total number of people in that column, referred to in the program as TOT symptoms. We are trying to calculate the chance that our patient is suffering from a particular disease, and all the people with that disease, regardless of the symptoms they do or don't show, are the ones in the row corresponding to that disease. We will need the total for that row, referred to in the program as TOT disease. There are a certain number of people, call the figure X people, who both have that disease and show the combination of symptoms sitting right in front of us. That's where the row for that disease intersects with the symptoms column and has the value X in it. And here's how we calculate the probabilities. In this case, population is the total number of people in that table, the total population of people, if you like. We get that simply by summing all the figures in the table. Right, the prevalence of the disease as a whole in society is found by dividing the total number of people with the disease by the total population. And the probability of some given person not having the disease is found by subtracting this figure from 1, since either a person has the disease or he hasn't. The probability that a person shows the combination of symptoms we're looking at, assuming that he has the disease, is the total number of people who both have the symptoms and the disease, that's X, divided by the total number of people with the disease. You'll notice that both the numerator and denominator of that fraction only consider people who are known to have the disease. Similarly, the probability of any person showing the symptoms, assuming that he doesn't have the disease, is found by dividing the total number of all the people who show those symptoms minus the ones who have the disease, by the total number of people in the population who don't have the disease. Again, there's a restriction in both the numerator and denominator of the fraction, though this time both are limited to people without this particular disease, although they might have a different one, of course. Finally, to the program itself. What you're looking at is the HTML code that creates one line of that table. It's the line for the disease Saturday Night Fever, where all the input fields start with the letters S, N, F and an underscore. Each of the element names contains a 3-digit binary number corresponding to that particular combination of symptoms, together with default values that I dreamed up. There are similar lines that start with the letters TGS, MP and H for healthy. The program needs 5 global variables. The string S, initially blank, is where the diagnosis of the disease will be built up. E is going to hold the 3-digit binary number representing the symptoms that the current patient is showing. I used E to be consistent with the Bayes rule equation, in which E stood for evidence. The variable population will hold the total population of people in that table, found by adding all the numbers together. I have also set up 2 arrays, one to hold names of all the rows, i.e. all the diseases, in the form of the acronyms, and one to hold all the combinations of symptoms that head up each of the columns. Putting an element from the row array in front of an element from the col array with an underscore between them allows the program to access any of those numbers in the table. The button Diagnose on the screen calls a function of the same name. The first thing that it does is to read the 3 checkboxes and translate them into a string of 1s and 0s. I use the ternary operator in each case, testing the checked property of each checkboxes. Note that the second and third lines of those 3 start with the plus equals operator, rather than simple assignment to string the digits together. The next 4 lines go through all the rows and all the columns, adding the figures that it reads to a running total to build up the total population. Note that when reading the value from the input field, you have to enclose it within the eval function. This is because the field contains a string, which just happens to represent a number. If you don't use eval, the plus operator will interpret the values as strings and will string them together to form a huge chain of digits. Eval ensures that the number values are added together instead. The function Disseez is used to determine the probability that the symptoms point to a particular disease, and it is called 3 times, once for each of the diseases under consideration. Finally, the results of these function calls, present in the string S, are copied into a division called Diagnose to display the final results on the screen. You'll notice that the disease name, or rather its acronym, is referred to by that parameter D in the function Disseez. As with E, I chose this to match the equations. There are 4 parts to the function. The first for loop, highlighted in red, counts the total number of people known to have this particular disease, which becomes top disease. The second loop, in blue, counts the number of people known to have this list of symptoms, storing the answer in top symptoms. Looking at it, I suppose that this could be more efficiently done outside the function, as the same figures will be needed for each disease in the list. It's only just occurred to me that top symptoms will be better off being calculated just once and stored as a global variable. Sorry about that. Another line calculates the value of x in the equation, which is the number of people with the disease in question and the current list of symptoms. Then the various probabilities are calculated according to those equations which I showed you earlier. You can see them all there, P of D, P of E given D, and so on. It is then a simple matter to calculate the final probability according to Bayes' rule, and to add it to the final diagnosis as a percentage. The function dp1 simply returns the value to 1 decimal place. And there you are. The program itself is rather simple, and so this video can be an unusually short one. It's difficult to think of any suggestions as to how you might like to extend this project, although it can be interesting to alter the figures in the table to see what extent that will change the diagnosis for any combination of symptoms. Making the project more complicated, turning it into a proper expert system based on probability theory, runs the risk of turning it into a Bayesian network, which is the topic of next week's lecture. So, having said that, it only remains for me to ask you to subscribe to the channel if you haven't already done so, share and like the video, and of course, comment below. Thank you.